Hello and welcome back to the video series about algebra, where we talk a lot about group theory. And indeed, in today's part 21, we will talk a lot about so-called normal subgroups. But as always, before I explain the definition, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, as a Steady or Patreon member, you can access a lot of additional material for the videos. For example, you can download a printable PDF version for the whole video course here. And then without further ado, let's immediately recall what we have already discussed as conjugate subgroups. This is important because, as I can already tell you, normal subgroups are also sometimes called self-conjugate subgroups. So it's definitely related to this notion that we have discussed in part 13. Of course, there we just need to consider a group G and subgroups in it. So let's take two subgroups U and V, and they can be conjugate if they satisfy a condition. And as you might remember, this is given by an inner automorphism for an element G. So more precisely, we define the new subgroup GUG inverse, and this should be equal to V. This means if such an element G exists, we call the two subgroups U and V conjugate subgroups. And you already know we say conjugate, but this is actually an equivalence relation on the set of subgroups of G. This is quite nice because we could say that V is equivalent to U if this condition here is satisfied, and we can look at the corresponding equivalence class. And there I would say, to make this more vivid, let's immediately look at a concrete example. And let's take the symmetric group S3, because there we already know all the subgroups. So here we have the group S3, which has 6 elements, and they can be written as E, AB, A squared, AB and BA. And now by Lagrange's theorem, we know that the order of a subgroup has to divide the order of S3. Hence the possible orders are just 1, 2, 3 and 6. So it's not a problem at all to list all the subgroups, and we can start with the trivial one. And here please don't forget, obviously if two subgroups are conjugate subgroups, the two orders have to coincide. This is quite clear because it's constructed in that way, and we have a symmetric equivalence relation, so it works in both ways. This means here in the trivial case, we already have the whole equivalence class for this subgroup. So this is quite simple, this equivalence class only has one element in it. And now let's go to the next order, which is order 2. There we have EB, EBA and EAB. So these are all the subgroups of order 2, and indeed in part 13 we have already shown that these subgroups are all conjugate to each other. In other words, in this case, they all lie in one equivalence class. So this equivalence class is bigger, it has 3 elements in it. However, now in the next case, for the subgroup of order 3, we only have one. This one is EAA squared, and you can check that this one is the only one. Which also means that this equivalence class only has one element as well. And then finally, we can go to the next trivial case, which is the whole group S3 as a subgroup. But as before in the beginning, there it's not a surprise that we only have one element in the equivalence class. However, in between, different things can happen, and this is how we distinguish normal subgroups from the other ones. In fact, we say that we have a normal subgroup if the corresponding equivalence class is minimal, so it only has one element in it. So this means that the conjugate subgroups actually give the unnormal behavior which we don't want. And I can already tell you, soon we will see why normal subgroups are so important. But before that, I want to write down the formal definition. So as before, we take any group G and a subgroup U of it. And now U is called normal if conjugating it does not change it. This means putting GUG inverse together always brings you to U again. This is why normal subgroups are also sometimes called self-conjugate. And obviously this equation should hold for every G in the group G. And with the discussion above, we can already state one important example. So the subgroup EAA squared is normal in S3. Obviously in S3 it's not the only normal one, but it's the only normal one which is non-trivial. This means we can already write down that the biggest and the smallest subgroup are always normal subgroups. So this holds in any group, which means these are not the interesting normal subgroups. Moreover, we also know that this conjugate operation here does not do anything in abelian groups. This means if everything commutes in the group, then all the subgroups are normal. Hence, in abelian groups, the term normal is not really needed. And now before I want to show you how you can use normal subgroups in general group theory, I first want to point out that there are different definitions in different books around. The reason for that is quite simple, they are all equivalent, but the formulation looks a little bit different. So as before, we fix a group G and we take a general subgroup U. And now I give you 4 equivalent statements for having a normal subgroup. Hence the first one is just the definition as we have chosen it before, U should be self-conjugate for every G in G. However, now it turns out we don't need to claim the equality here, it's good enough to have the subset relation. This means for any G in G, this conjugate combination just lies inside the set U. So this does not change anything, and now you might also believe me that we can bring G inverse to the right hand side. So what we get here is that the left coset is equal to the right coset no matter which G in G we choose. And seeing that, you might remember that the left and the right cosets are related to equivalence relations on G. For example, we can call two elements A and G equivalent if AG inverse lies in our subgroup U. This is related to the right coset, and if you want a relation to the left coset, you have to consider something like A inverse times G. And now the good thing is that for a normal subgroup, both things are actually equivalent. Even more, as you can see here, you could use this statement here as the definition for a normal subgroup. Now showing these equivalences is actually not so hard, but we will do it anyway, such that you get used to these operations. First of all, 1 implies 2 is already given in the definition of the subset relation. Hence the interesting part is just going from 2 to 1. So now we assume that we have the subset relation for every element G in the group G. This means if we fix such a G, the relation also holds for the inverse of G. So we can also write G inverse UG is a subset of U. And there you see this is the only thing we need to do, because now we could bring G to the right hand side again. However, maybe the whole thing is easier to see if we go to the element level, so let's fix a U in our subgroup U. And since we have the subset relation above, it also tells us that we find a V in U as well. This means we have our U in the combination on the left hand side, and this is equal to the V on the right hand side. So this is exactly what the subset relation tells us. For every U, we find such a V. And there on the element level, you see there's no problem at all to bring G to the right hand side. So you see, U can be written in this form, which means that U is actually an element in this set. And there we have it. We start with an element in U, and then we show that it also lies in this subset. So in other words, now we also have shown the second subset relation. So there we have it, 1 and 2 are definitely equivalent. And indeed, in a really similar way, we can also show that 1 is equivalent to 3. Essentially, it's again just bringing G to the right hand side here, but maybe it's easier to see if you write it in the element level again. So to keep it simple, we could say the set here on the left hand side is given by G UG inverse, whereas our lowercase u goes through all the elements in U. And obviously the right hand side we can also write in such a complicated way. And now maybe to not get confused here, we could also use a V instead of U on the right hand side. For the sets it does not matter, but if you want to write it as an equality for the elements, you would have GUG inverse is equal to V. And since we have this equality for all the elements U and V in U, we can multiply both sides by G from the right hand side. Since we work in a group, this is equivalent, and we can write the set here just as GU now. And obviously on the right hand side here we have VG. So there you see, this is how we quickly get the set equality, and if you're not happy with this short formulation, you can also write down the whole thing with the implications like above. However, I already think it's quite clear, we have the equality of the two sets. Here we have the left coset and there the right coset. So there we have it, and you can already remember, only for normal subgroups we have that the left coset is equal to the right coset. And exactly this nice fact for normal subgroups we will use in the next videos. But first let's finish the proof here, which means we show the last equivalence, and let's start with the first implication 3 to 4. So we assume that we have this equality of the two cosets, and then we can just calculate with the elements. This means we take A and G as elements in the group G, and we start that AG inverse lies in U. And now obviously by multiplying with G, we see that A lies in the right coset. So this is a similar calculation as before, and now we can also look at the second statement. There we just have that A inverse times G lies in U. However, since U is a subgroup, we can also look at the inverse of this element, and it also has to lie in U. And we can just split it up, and you see what we actually have here is G inverse times A. Therefore we can just multiply with G from the left, and we get that A lies in the left coset. And now since we assume that the left and the right cosets coincide, we also have the equivalence here on the right hand side. So not so complicated, this one shows the equivalence stated in part 4. So you see we are almost done, we just have to show the last implication 4 to 3. So let's fix the element G in G, and let's assume that we always have the equivalence stated in 4. This means AG inverse lies in U if and only if A inverse G lies in U as well, and this holds for every A in G. And now as stated above, we can reformulate that with the left and right cosets. So the left hand side here says that for all A in G, we have that A lies in the right coset UG, and as already discussed, the other one is the same statement but with the left coset. So you see these are statements for all elements in a given set, so actually here we have a set inequality. If all the elements of two sets coincide, we know that the two sets are the same. There's no other way, UG is equal to GU. And this finishes the proof, and it explains why different definitions for normal subgroups are possible. They are just all equivalent, as you can see with these more or less simple steps. Essentially you just have to justify that you can extend the group operation to the sets as well. And then in the end, on the set level, we actually get a commutation rule. And that will allow us to use normal subgroups to define new group operations and new groups. And there I would say, let's look at these new constructions in the next videos. So I really hope I meet you there again, and have a nice day. Bye bye.